SN to TH reaction. Today I will show you that rule and after Zerevitnov's method. See here JEE Mains 2025. 90% JEE students memorize Grignard reactions, but one rule decides every question. Hello students, let us start. Grignard's reagent in one shot. It is an organometallic compound with the general formula RMgX, where R is alkyl, aryl or vinyl. Mg it is magnesium, halogen, chlorine, bromine, iodine. Preparation see here, alkyl halide when allowed to react with magnesium triether, RMgX is formed. Stability of Grignard reagent directly proportional to stability of C minus produced by Gr, which is C minus here, R minus, whatever produced by RMgX. For example, here if you observe it, Grignard reagent stability. So here CH3MgX, CH3CH2MgX are respective compounds given. Stability of R minus produced by Grignard reagent. So how to find? In every case, we break it minus, break it here minus, minus, and here it is minus. We know here primary carboanion, secondary carboanion, tertiary carboanion. We know primary carboanion is more stable than secondary, tertiary. So here, based on negative charge C minus, we can predict the stability. So overall, if you see CH3 minus more stable than CH3 CH2 minus, secondary and then tertiary carboanion. Stability of Grignard reagent. Grignard reagent act as strong nucleophile as well as strong bases. They must be prepared and used in dry conditions because water destroys them. If any water moisture destroys reagent like this, RMgX react with H2S, H2O to form hydrocarbon and other compounds. So destroying Grignard reagent if any water. It should be in dry condition you have to use. Ri, RBr, RCl, rate of reaction towards formation of Grignard reagent. So Ri is more reactive to form Grignard reagent. Dry ethers are used as solvents for Grignard reagent. Ether has lone pairs on oxygen which coordinate with magnesium and stabilize RMgX. See here RMgX, diethyl ether, so oxygen having lone pairs. Magnesium electron deficiency, that is compensated by electrons of oxygen. So electrons of oxygen form coordinate bond with magnesium, hence electron deficiency of magnesium neutralized and become stable. All ethers are good solvents except cyclopropane ring like 3-membered ring with oxygen, heterocyclic compound, 4-membered with oxygen inside the ring as they react with Grignard reagent. Best solvents, tetrahydrofurane as well as tetrahydropyrane. These two are best solvents. Polar protic solvents are not good solvents because polar protic solvents like water, they react with Grignard reagent, form alkane. Acid-base reaction they show. Polar aprotic solvents, which are polar in nature but cannot produce hydrogen. Polar aprotic, even these cannot be used as solvent because they react with RMgX. Nucleophilic addition reaction occurs. It adds to RMgX. So reaction occurs. Why not good solvent? Because they react. Simple answer. Chemical reactions of Grignard reagents. Acid-base reactions of Grignard reagent. So acid-base reactions like RMgX, the one which can produce H plus like H2O, alcohol, or acids, phenol, alkynes, cyanide, thiol, amines, secondary amine, carboxylic acid, sulfonic acid. Such compounds readily produce hydrogen. So here R react with hydrogen of such compounds like this, H2O, RH, alkane formed. Here also ROH gives H plus, alkane forms. Similarly, all these compounds, any one compound allowed to react RMgX, it forms alkane because they produce hydrogens. D2O, it gives D, it produces RD, MgODX. Zerevitnov's method. So Zerevitnov's method, why we use? It is used to determine the number of active hydrogen atoms present in an organic compound. Number of active hydrogen atoms we use. To find number of active hydrogen atoms present in organic compound, we use this method, Zerevitnov's method. What is this? See, a compound containing active hydrogen reacts with Grignard reagent to produce methane. Like for example, number of moles of methane or volume of methane evolved tells you how many active hydrogens are present. What see here? Active hydrogens include OH like alcohols, phenols, COOH, OH from any of these compounds, NH amines, amides, SH thiols, terminal alkynes like the hydrogen is active hydrogen. For example, if I take ethanol reacting with CH3MgI, most commonly we use CH3MgI here, methyl magnesium iodide. So as we know, it can produce active hydrogen. So active hydrogen combined with The hydrogen that is coming from combine with CH3 minus and finally it forms methane. If it is giving one hydrogen, it forms 1 mole of methane. Rest over like MgO-C2H5i. Number of active hydrogens is equal to number of moles of methane. For example, see here, ethylene diol or ethylene glycol, common name, 2 active hydrogens. 2 active hydrogens combine with excess methyl magnesium bromide. If I take methyl magnesium bromide, so now here it combine with, we are taking here excess amount, it will combine with 2 hydrogens and form 2 moles of methane. So this confirms that 2 active hydrogens present in the reactant, whatever given here. Okay. Next, nucleophilic addition reactions. Nucleophilic addition reactions is aldehyde or ketone. RMgX gives R minus. So if oxygen takes pi electrons, here positive charge developed. At positive charge, R minus attack. So after attacking R minus, O minus Mgx attack here. So now hydrolysis, H2O breaks the bond. So we add here OH and then Mgx here like this. Secondary alcohol we are getting, Mgx OH here attached. Secondary alcohol. Rate of nucleophilic addition. See, nucleophile is here R minus. Directly proportional to amount of positive charge at CO. Here you have to see positive charge at CO. For example, see here. Here it is positively charged. Here the positive charge neutralized by plus I group. Here also positive charge neutralized by plus I group. CH3, CH2. So more is the positive charge, more is the rate of nucleophilic addition. But where there is more positive charge, first compound because second and third, because of plus I effect, it is neutralized. Positive charge. Hence, rate of reaction, nucleophilic addition 1 greater than 2 greater than 3 in this question. Okay. Next. See here, example we showed CH3CHO RMgX H3O plus. RMgX H3O plus. Now here it is giving CH3CrOH. What we did? Just add R to C. We are getting an H3O plus gives what it gives. Like hydrolysis, finally it gives hydrogen to the compound. O minus. Here H plus attaches, OH we got. Similarly here, one equivalent if we take, one equivalent. So two CO groups, but among these two where it attacks. Here CO group present, but the positive charge of CO suppressed by, neutralized by plus I group. But here positive charge is as it is because there is no plus I group here. So wherever there is more positive charge, there R minus attacks. So after attacking, R we have to, methyl we have to add. After hydrolysis, O converted to OH. As it is chiral carbon, where carbon is attached to 4 different groups, here you will get optical active mixture, that is optical inactive racemic mixture, plus minus mixture you will get. Plus is dextroisomer, minus is levoisomer. Mixture of these two will give racemic mixture, optical inactive overall. Here you see, here what you will get, methyl magnesium bromide. So here as it is, here oxygen gets H plus from H3O plus, Me attack here, Me. Right? Possibility, either it can attach from here or other side if you see, if OH forming here, hydrogen at other side, methyl here. So possibility, both are getting diastereomers. They are getting both. Here these are not mirror images. So non-superimposable, non-mirror images are diastereomers. So non-mirror images are diastereomers here. Possibility, either it can form OH here or other side, diastereomers. SN to TH reactions of Grignard reagent. SN to TH meaning tetrahedral intermediate. TH means through tetrahedral intermediate. Like acid derivatives, acid halide, anhydride, ester, amide. These compounds shows SN to TH through tetrahedral intermediate reaction passes. So you see general formulas. So rate of SN to TH directly proportional to amount of positive charge at CO. Same like above. Here positive charge you have to show at CO. So if you observe it, here there is more positive charge at CO, rate of SN to TH compared with remaining two. Here positive charge, here even oxygen lone pairs, plus some effect. Here it can give electrons to C double bond mode because of plus some effect of other group. Positive charge and carbonyl group decreases. Here also same. See here, this side even other side also plus some effect decreases. So here there is acidic hydrogen. Actually, this particular amide will not show SN to TH. It will show acid-base reaction because of acidic hydrogen. This hydrogen is acidic hydrogen, so it will not show SN2TH, but it will show acid-base reaction. Acid-base reaction is hydrogen, it gives R minus combined with this. See now. RMgX, it is slow step in this mechanism, you see. R minus attack here. R minus attack here. Right? And the X are group G or X here. Anyway, you can specify. So this particular group or X detach from the carbon because O minus comes back again, detaches X. So in fast step, G minus removed. So after rebalancing O minus, you will get here ketone. Ketone you will get. Finally, it is tetrahedral intermediate in between. So reaction passing through tetrahedral intermediate, that's why it is SN2TH. What is SN2 reaction, nucleophilic substitution reaction, will be studied in detail after this video. Next upcoming video, that is based on nucleophilic substitution reactions SN1, SN2. After completion of some important facts about alkyl halides, aryl halides. Next, here observe it. Amides cannot give SN2TH reactions as acidic hydrogen gives acid-base reaction. But substituted amides without acidic hydrogen can give reactions like above. See here, NH2 hydrogens present. If no hydrogens, if hydrogens replaced by any alkyl group, then it can give SN2TH. As usual, R minus attach here, remaining part you remove it. So remember, amides with alpha hydrogens or acidic hydrogens cannot show SN2TH, but if it is substituted amide, it can show. Okay, acid chloride, see here, methyl magnesium bromide, one equivalent. So you will get methyl group here, removal of Cl. Excess amount if I take, one methyl here, in place of chlorine, one more methyl. In place of, so one methyl, here we showed, but one more methyl by moving oxygen side, double pi bond. So here one more methyl added, followed by H3O plus gives H plus, finally we are converting into OH. OH. So whenever it is excess amount of methyl magnesium bromide taken, two methyl groups added. Grignard reagent, excess H3O plus alcohol product. So what is ester here? Product alcohol may be. Product alcohol may be. So what kind of alcohol you can see? See here. Grignard reagent excess meaning two alkyl groups come from Grignard reagent. Two alkyl groups like this. Two alkyl groups coming from excess reagent. So at least two groups should be same. At least two groups should be same, like pH. Here also, see here, product of alcohol, see ethyl, any combination you can take, like Grignard reagent, how you can take? pH MgX, it may be aryl also, or you can say ET MgX. So if it excess two ET groups, you will get, if I take pH MgX, two pH groups, CH3 MgX, CH3. But here see, three groups are different. No, we need two groups should be same. At least two groups should be same because those two groups coming from excess Grignard reagent. Here see, no group is same. So it is not possible. Remaining two may be product. Reason is, as we used excess Grignard reagent, at least two same alkyl groups should be in product. Either alkyl or aryl if you use aryl compound. Okay. Same alkyl or aryl. Anyone, whatever used in reaction. Oxygen, that is COCl2, methyl magnesium bromide, excess if we take here, C. What happens? C. Here, we remove both the chlorine atoms. Both the chlorine atoms removed. So, methyl magnesium bromide, methyl. So, three methyl groups and followed by H3O plus gives H plus, three methyl groups and OH. Oxygen. Important reaction, remember. SN2 reactions of Grignard reagent. SN2 reaction that we are going to see. Next video, we are going to see what is SN1, SN2 reaction. Presently, just to focus on the mechanism, whatever we studied in this case. With epoxides, methyl magnesium bromide, SN2. So, methyl attacks at less crowded side. Methyl attacks at less crowded side, which is oxirane. We call it as oxirane. Like this one. This one is oxirane. Less crowded side attacking here. So, methyl is attached here. Then H3O plus if you add, it becomes OH. Overall methyl already exists, one more methyl added, it is the product. Remember, methanol and ethanol cannot be prepared by this method. As we know, here only one carbon, here two carbons in this. So more than that you will get in this method. SN2 with RX. SN2 with alkyl halide C. RX R dash X if I take SN2. So here RX R minus R dash combine, they form alkane MgX2. And remember here SN2 with RX R dash X, this one should not be equal to tertiary alkyl halide, bridge compound alkyl halide, aromatic alkyl halide, vinyl halide. These will not show SN2 reaction because of stability factors. So remember, this alkyl halide should not be equal to tertiary, bridge one, aryl halide, vinyl halide. They will not show reactions. For example, see, aryl magnesium bromide CH3Br. So here Grignard reagent reacting with alkyl halide, so reaction possible. What we do here? This one minus combine with CH3. Overall, you get this one. But in this case, PHBr will not show reaction. Not feasible. Why not feasible? Because you can check here. These aryl halide, this one, aryl halide will not show reaction because the breaking of this bond is much more difficult here. Breaking of this bond because of resonance. Double bond, the pi electron, that is lone pair electrons show resonance with the ring. So double bond character develop, partial double bond character, difficult to break. So such reactions not feasible. Reaction with Grignard reagent CO2. So here directly CO2 and H3O plus. Mechanism I showed see here. RMgX C double bond O. So here after shifting of pi electrons other side, COO minus. And then after that, here R attack here carbon, then HOH. Finally, you get carboxylic acid. Remember, whenever CO2 Grignard reagent, carboxylic acid is formed. Similarly, RMgX carbon disulfide, here you get this product. Like RCOOH, here it is RCHS. Same like CO2, here also reaction. There hydrogen we showed, here also hydrogen, remaining as it is. SO2, here you get RSO, here also same. Like CS2, SO2, C double bond, same. One extra hydrogen we are adding. CO2 H3O plus, reaction C here, PHCOOH. Reactions of Grignard reagent with O2. So O2, what happens is see here. Mechanism not so important. Just for reference purpose, I gave here O2. Here chelation, that is ring formation observed. Ring formation type. Then finally again one more R minus MgX combining with ring chelation. Finally it forms alcohol. Mechanism not important. No need to remember mechanism. Just to remember, whenever oxygen H3O combination Grignard reagent, it gives alcohol. Whenever CO2 H3O combination Grignard reagent gives carboxylic acid. Those conversions, if you remember, more than sufficient. See here O3 H3O MEOH, O2 H3O plus ETOH, O2 H3O plus BHOH, always alcohol. Reactions of Grignard reagent with RC triple bond N. Here also mechanism I gave, mechanism not so important. You focus on overall conversion. What's happening here? Cyanide on reaction with Grignard reagent gives ketone. It is giving ketone. Here I showed mechanism how ketone is formed for reference purpose. But main important only here remember the conversion. Cyanide, here it is ketone. HCN, it can produce acidic hydrogen. So it's not like ketone. Acidic hydrogen we know. Whenever acidic hydrogen, it gives acid-base reaction. Stable Grignard reagent cannot be prepared if it has acidic hydrogen, XY unsaturation, CX bond. Why you cannot prepare acidic hydrogen? Reacts further. These conditions make Grignard reagent to react. Hence, we cannot prepare stable Grignard reagent if any of these available. For example, see, this particular reagent we are using to prepare Grignard reagent by in presence of magnesium triether. Here, the resultant compound having acidic hydrogen, OH. If resultant compound having acidic hydrogen, unstable, it reacts further and form another compound, see, ethoxy magnesium halide. It's not a Grignard reagent. Further reaction occurs. Mono Grignard reagent is not possible with dihalides. For example, if I have dihalides, magnesium 1 equivalent, you will get unstable halogen, unstable compound. Here what happens? Halogen removed, C minus attacks here. Internal shift occurs and cyclic ring is formed here. 5-membered cyclic ring is formed in this case. Okay, that's why it is unstable. So you cannot prepare mono Grignard reagent because of unstable condition, dihalides. Okay, this particular compound is formed. Next, actually here 5 carbons. You can specify here 5 carbon. That's why you are getting 5-membered ring. 5 carbons. Grignard reagent. So preparation you see here. 2 dihalides we are taking. Magnesium excess ether. So everywhere magnesium X, 6-membered ring is formed. So which is Grignard reagent. 2 Grignard reagent groups. Reactions of Grignard reagent. What we do here? For example, ester taken. Here we remove OET, oxygen shifting electrons towards itself. So after that RCO OET, here it attacks with this one RMgX, means 2 times Grignard reagent. Here ETOH formed from OET. So remaining part, here hydrogen added to this ROH. So remaining 4-membered 1, 2, 3, 4. 4 carbons will form ring with respect to this. Cyclization occurs. Here as a C. Here phosgene if we take Grignard reagent, sorry, MEMGBr. So here what you will get? All chlorine atoms and even one more extra methyl OH. H3O plus gives hydrogen. It's not Grignard reagent. It's like normal methyl magnesium bromide reaction. Okay. Next. See here JEE Mains 2025 magnesium diether H2O RBr 2-methyl butane. The maximum number of RBr producing 2-methyl butane by above sequence of reactions is dash. Consider even structural isomers only. See. So here how to identify answer here? So RBr Mg diether H2O. So we are preparing by using alkyl halide magnesium diether. So here maximum number of RBr producing 2-methyl butane by above sequence of reactions. 2-methyl butane is structural isomers also we need to think. So how we will get here? Magnesium diether we know reaction. It combine with magnesium diether H2O. So Grignard reagent it is RBr. So what we are going to get here? Whenever magnesium diether, what are the products you see here? For example, RBr, if you are adding magnesium diether, here you will get RMgBr, Grignard reagent you will get. After that on hydrolysis, and hydrolysis you will get RH, which is alkane. We know this reaction, just now we studied above. So how many isomers of RBr will give 2-methyl butane? That is 2-methyl butane. So possibilities you see here now. RBr may be, as they mentioned, 1, 2, 3, 4, 5 carbons they mentioned. So possibilities you see here. So here there is one possibility to give that 5 carbons. One more possibility, you can place Br here. Second, you can place Br here. Third, overall 4 carbons we need to see here. 4 carbons should be from the reactant side because 5 carbons. And next, another possibility, see 1, 2, 3, 4, 5. Here there is Br. The different structural isomers we are placing. Overall here 4 structural isomers possible. Overall 4 possible to give the product. Answer is 2 here. Okay, structural isomers you have to frame. Next, JEE Advanced 2014 question. CH3MgBr diether aqueous acid they mention. Aqueous acid. So observe question here, what they gave. So in this case, reactant that is given CH3MgBr, again Grignard reagent. So what happens? Grignard reagent first attacks CO group, that is carbonyl group, we know. So which gives, what it gives first? See here. After reaction, first it gives, as it is Cl, here no change. Here you will get same number of carbon atoms you mentioned. After that, just a minute, I will show you here. See, after the reaction, Cl as it is reactants. So here you will get OMgBr, OMgBr as well as CH3. Here CH3 attack, right? Here that is CH3 from CH3 MgBr. We know already how to frame reaction. After that, the alkoxide ion attacks the terminal carbon having chlorine. This alkoxide ion attacks terminal carbon having chlorine. So what happens now? So here OMgBr CH3 CH3. So here what you will get? C1s now. CH3 CH3. This alkoxide ion attacks this one, the terminal carbon where halogen, so positively charged. If it attack here, cyclization occurs. 5-member cyclic ether formed. 5-member cyclic ether. So here further on cyclization, here it gives joins and CH3 as it is. Cyclization. So which should be option D. Cyclization occurs further so that 5-member ring is formed, which is 2,2-dimethyl, tetrahydrofurane. Okay. I hope all the questions clear to everyone. See, next video that is based on alkyl halides, aryl halides series, we are going to discuss one by one. First, alkyl halides, aryl halides having SN1, SN2. That is most important video lecture. So after completion of these videos, try to watch even alkyl halides, aryl halides series. Thank you. For more updates, follow the channel.